in chapter 6. And you can see there in figure 6.4, the precursor to what is on page 282 in chapter 8. So he derives the path integrals using stuff that he's already done, that is building on earlier chapters with the time propagator that we've already developed and so on. And he quite rightly says this is not the way Feynman did it. I'm going to do it the way Feynman did it because it's more fun. And also, we get at the end of this development to derive what my PhD advisor used to call the Schrödinger algorithm. Anyway, kind of cute. All right, so what is the two-slit experiment? I mean, the idea is you have some sort of source of quantum particles. Here, I'm trying to draw a hot wire that emits electrons. Okay, and then over there, I'm gonna put some sort of voltage across the whole apparatus so that the electrons want to go in this direction. And then we have a screen with two slits in it, which I'm trying to draw here. And then over here, we have a line of detectors, right? Or a screen of detectors or something. And what we get is an interference pattern, which I can't draw very well, but I'm giving it a shot, which looks something like that. Okay. It's an interference pattern, okay? So this, quote unquote, illustrates what's vernacularly known as the wave nature of quantum mechanical particles. And this will work with electrons or photons or, any quantum particles. It won't work with bullets, okay? If you were doing bullets, what would you get? Well, you'd get a peak centered around this, or opposite this slit here, and a peak opposite this slit here. That's what you'd get if they were bullets. So this is bullets, and this is quantum particles exhibiting interference. So what's the mathematical feature? Okay, if we're exhibiting interference, then we are not obeying the Laplacian rules of classical probability, i.e. Laplacian probability rules wrong. Okay, so bullets have Laplacian, and what I'm going to sort of, let's call these slits slit 1 and slit 2, right? If this were exhibiting Laplacian probability, then the probability of going through 1 plus the probability of going through 2 would be the probability of going through 1 plus the probability of going through 2. Sorry, that didn't come out very well. What I mean is, if both slits are open, I'm going to call that P12, then the pattern I get is the pattern I get if only slit 1 is open, plus the pattern I get if only slit 2 is open. But with quantum particles, as you know, quantum probability doesn't work that way. Instead, we have something we call a probability amplitude. Let's call it phi. Phi1 if slit 1 is open, and phi2 if slit 2 is open. And what you get for if both slits are open are phi1, 2. And how is this related to classical or Laplacian probability? Well, it's related to that by P1 equals phi 1 squared, absolute magnitude squared. P2 equals phi 2 squared, absolute magnitude squared. And, excuse me, and P12 is equal to phi 12 squared equals phi 1 plus phi 2 squared. In other words, there is interference. There are interference effects. And you can check this experimentally by doing exactly that experiment. That is, let's close off 2 and see what we get. Well, if we close off 2, then we're only going to get phi 1, right? What do we get? We get the red thing. If we open 2 and we close off 1, what do we get? We get the red thing. This red thing. So this really is P1 and P2, but if both are open, I don't get P1 plus P2. Instead, I get this interference pattern. Now, the obvious non-quantum mechanical answer that you'll get from, you know, a bright child to whom you're presenting this stuff is, well, okay, so the electrons are interfering with each other, right? And that's actually wrong. How do we know it's wrong? We know it's wrong because we can do that experiment. We can reduce the flux here so that the probability that there's more than one electron, or photon if you like, in the apparatus at any one time is essentially 0. Okay, so you just reduce the flux, and then you just wait a heck of a long time for the interference pattern to build up, and it will. It'll build up photon by photon or electron by electron until you get the interference pattern. So it can't be that the electrons are interfering with each other. It must be that the electrons are interfering with themselves. So what's the picture we have in our heads? The picture we have in our heads is something like this. As if the electron, each electron, were in fact a wave. Such that when it hits a slit, it does like this. And these waves interfere with each other. But you get two sources of waveness from each of the two slits. You get a source of waveness from only one electron at a time, or from only one photon at a time. And that's the only way we can make sense of these experimental results. And these, you know, these experiments have been done. So I'm not just making this up. Quantum mechanics is actually real. It's so complex. Okay, so experimentally we know that this mathematical model actually works. That there's something that we like to call a quantum probability amplitude, which, when absolute magnitude squared, gives us a classical probability. Okay, great. How do we understand that? Well, there are many different ways of understanding it, and it turns out that mathematically they're all equivalent. So, for example, the Schrödinger method, or algorithm as my boss used to say, is equivalent to the Dirac matrix method. And we've talked about that since chapter 6, when we actually introduced the Schrödinger algorithm. Well, in terms of waves, that is. Well, what do we do with this guy, which is a new way of understanding this? Well, it turns out that the Feynman path integral method is another equivalent way of understanding quantum mechanics. It's equivalent to Schrödinger, it's equivalent to Dirac, and we're going to see exactly how that works. Personally, I think it's really beautiful because it contains not just quantum mechanics, but also classical mechanics, so that you naturally get the classical limit. Feynman gives credit to Dirac for the seed of the idea when he points out in a paper, I think it's from the 1940s, hold on, I've got the citation here someplace. Yeah, 1943, anyway, Dirac pointed out that the Green's function e to the is over h bar is a good solution, is a good approximation, not just for very, very, very almost classical h bar, but also for very, very, very small t. So we're going to do this. We're going to do the derivation of this Feynman path neural method in Feynman's way. Okay, so how does that work? Well, basic idea is that we do our two-slit experiment, and I'm just drawing it again for you here, very badly. All right, close enough. And here's the detector over here. Right. As Townsend points out on page 282, one way of understanding this is, and I'm going to use a slightly different notation for what he does, I'm going to call this this one the right-hand side and this one the left-hand side. So instead of calling them slit 1 and slit 2, I'm going to call this screen 1 and this the left and this the right. So what you can imagine is dashy, 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 dashy. What I'm doing here is creating a two-state system. That is, I'm only going to look to see whether the quantum particle, the quantum system, is on the left or on the right. And I'm doing that by sort of turning my head like this, so this is left and that's right. How's that? Okay. So now what do? Well, we introduce another screen. It's supposed to be exactly the same as this screen, just over here. Again, the particles can be going through the left or the right. And we introduce another screen. These are all supposed to be identical. And another one. And now we see what Townsend is talking about here, the idea of a path, right? We are actually dividing up the space, the physical space, into two sort of bins, the left-hand side and the right-hand side, okay? So we can imagine that a quantum mechanical particle, in order to get to this screen, well, it can go left and then left and then left and then left and still be on the left. Or it could go left and then right and then left and then right and then left again. Or da 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 da, all right? Every time I put in a screen, I have two more possibilities. So I have number of screens, let that be, what did I call it in my notes? P or N or, I've forgotten. Okay, so let the number of screens be N, then there are 2 to the nth different possibilities. Everybody sort of okay? So what are we going to do here? Well, we're going to say, say that these are independent probabilities, independent possibilities for each particular path. Okay? So we're going to say that the probability amplitude for going from here and then to here is the same as the probability amplitude for here and then the probability amplitude for here. Just like if I were rolling a die and I did it sequentially, then the probability of getting a 1 on the first roll and a 1 on the second roll would be the probability of getting a 1 times the probability of getting a 1. Okay, so classically, in classical probability, I guess I should go back to red for the classical probability. In the classical probability, we would say that the probability of A and B is equal to the probability of A times the probability of B. This is an AND, a logical AND in classical probability. Okay. This is if those two events are independent of each other. And the fact that this is true means that they're independent of each other in classical probability. That's what we mean in classical probability by saying A and B are independent, is if their probabilities multiply. Okay. And so I'm just going to write this down. A and B are independent events. So that's what we mean by that. Okay, so what's the that's the class. What's the quantum mechanical analog to this? Well, the quantum mechanical analog is that the amplitudes would multiply. Okay? So the analogy is, or the corresponding thing quantum mechanically is, phi of A and B equals phi of A times phi of B. So far, so good? Okay. So the structure of this phi thing is simple if we accept that this is the law of probability, right? And the postulate that different legs of a trajectory are independent. And as long as the time segments are short enough, we can then multiply all these things together. Right, so that's the procedure. So then we would say that phi n, let me just copy my notation here so I don't screw it up, of, let's say we want to find out what the probability is of an electron or a quantum mechanical particle switching from the left-hand side to the right-hand side. So we want prob of switching from left to right, or right to left. By symmetry, it's the same thing. Okay, so what I'm going to say is that the total amplitude for the event that we're looking for is being on the left at time 0, times alpha 1 at time delta t, and then in state alpha 1 at delta t, and then in state alpha 2 at 2 delta t, and then in state alpha 3 at 3 delta t, dot, 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 right at n delta t. What did I call it? Yes, in fact, I did call it n delta t. N, little n. I shouldn't be switching all these notation. So that's what I want. And so I'm going to write down this probability amplitude, and then at the end I will absolute magnitude square it to get the probability of a total switch. Okay, well what's this alpha 1, alpha 2, alpha 3? Well, that's the state of the system at an intermediate time. And I have to sum over the two different possibilities of its being on the left or the right. So I have to sum over alpha 1 equals left and right, alpha 2 equals left and right, etc. Dot, dot, dot. I have to sum over all the trajectories that describe the event that I'm trying to find out the probability for. Okay, so with these assumptions, and what are those assumptions? The assumptions are that the legs of the trajectory are independent of each other, right? And that this is true. So two assumptions. One, phi of A and B equals phi of A, phi of B, for A, B in depth, and two, different time segments are independent. So if you assume these two things, all right, then this is the thing we want to calculate, and we can actually write it down. This is going to be the sum of the, I'm going to call it K. The probability amplitude to be on the left at 0, times the probability amplitude to be at alpha 1 at time delta t times the probability amplitude to be at alpha 2 at times delta t, 2 delta t, excuse me, dot, dot, dot. And so with these assumptions, we've reduced the problem to the problem of finding out what this is, or this, whatever. So for short times only, okay? So now all we need is the amplitude for short times. Let's call it delta t. And we're going to let delta t go to 0. In other words, what we're imagining is an infinite number of these two-slit screens. The screens don't have to be there, okay? They don't actually have to be there because we're just imagining, well, it can be on the left or it can be on the right. And we're just going to sum over all the ways it can do that. Okay, so what is this object that we're trying to find out? Is it okay if I erase this? Yeah. I never seem to get it as clean as it is before I start futzing about it. Okay, so what do we want? We want k that goes from alpha sub I at time I, let's call it tau I, to alpha I plus 1 at time tau, let's just call it tau, tau plus delta t. So that's what I want. So what is this object? Well, this object is a 2x2 matrix. Okay? What I need is 4 numbers. What are those 4 numbers? I want the amplitude to go from the right to the right in time delta t, from the right to the left in time delta t, from the left to the right, time delta t, and left to the left. I want 4 numbers. Because with my truncation here of space into either being on the left or on the right, I only have 4 possibilities. It either stays on one side, there are 2 ways you can do that, or it goes from one to the other, and there are 2 ways you can do that. So let's write this as a matrix, K, right? So this is a matrix. K, R, R, K, R, L, K, L, R, K, L, L. Okay, in time delta t. Okay, so now let's talk about making delta t really, really small. Okay, and you'll recognize this argument because we've used this argument in practically all the chapters we've done so far. Right? If delta t is 0, then the particle doesn't have any time to go anywhere. So if delta t is 0, then this is the identity matrix. Because it doesn't have any time to go anywhere. It can only just be where it is. But what we're going to do is we're going to expand this in a Taylor series. I thought this would be, I knew this was coming. So I'm going to say that it's going to be the identity matrix plus delta t times, you know, some other matrix, okay, to first order in delta t. So this is to 0th order in delta t, to first order in delta t. I'm going to write this as 1, 0, 0, 1 minus I over h bar, which is just a constant I'm taking out, times HRR, HRL, HLR, HLL. And I'm not telling you why I'm calling it H, but you could probably figure it out. other words, I'm writing this to first order in delta t as 1 or I minus I over h bar h, where I and h are matrices. Okay. All right. How does that give us our answer? Well, that gives us our answer because this product here is now just becoming a product of, let's call it I minus I over h bar h alpha I plus 1. And again, we're summing over this is a product over the segments I, and it's a sum over these states alpha I equals right or left. So this very messy thing has become very, very simple. Okay, it's going to become even simpler because we're going to see that we have restrictions on what the elements of H can be. Because why? Well, first of all, they can't be arbitrary complex numbers. Okay? Why not? Because the absolute magnitude of this phi n must be a probability. So it must be conserved. Okay? So are the elements of H arbitrary complex numbers? No, because phi n absolute magnitude squared is a probability which must be conserved in time. Okay, so what does that mean? Well, that means that the amplitude to be on the right at any one time squared plus the amplitude to be on the left at any one time squared has to equal 1. There are only two possibilities, it's on the right or it's on the left if it exists at all. Okay? So no matter what the previous amplitudes were, at any time, that must be the case. Right? So phi r at any one time is KRR phi, excuse me, let's call it, so this must be true irrespective of what the amplitudes were delta t before. Let that be psi. We have absolutely no imagination whatsoever. So we've got psi r and psi l. So phi r is KRR psi r plus KRL psi l. That's the amplitude to be on the right in terms of the amplitudes to be on the right and left one instant before, one delta t before. And phi l has to equal KLR phi r psi r plus KLL psi l. In other words, the amplitude to be on the right now is the amplitude that I was on the right an instant before times the probability amplitude to stay on the right plus the amplitude that I was on the left an instant before times the probability amplitude to go from the left to the right. Okay, so now I'm going to absolute magnitude square that. And I know that, I actually worked this all out, you believe me? So I'm going to do this. So this absolute magnitude squared and this absolute magnitude squared, I'm going to add them together. So this plus this has to equal 1. So 1 has to equal KRR psi r squared plus KRL psi L squared plus KRR psi R KRL psi L. That's the cross term, right? And this is going to be, sorry, on the one cross term I have these guys, and on the other cross term I have the other guys. So KRR psi R KRL star psi L star. Everybody sort of okay? And then the other term, KLR psi R squared plus KLL psi, that's an R, L squared plus KLR star psi R star KLL psi L plus KLR psi R KLL psi L star. Oh, 1, 2, 3, 4, 5, 6, 7, 8 terms. Okay? But I can summarize those with, I mean, I don't have to write them out. I can, but I don't have to. Because why? Because this is the same thing as the matrix K times the vector psi, dagger, times the matrix K times the vector psi, undaggered, where the dagger means the complex conjugate transpose. Okay, so that's the same thing if you flip it around and you do each individual thing, right? So this is the same thing as psi star K, sorry, not star, dagger, K psi. And that has to equal 1. So what have we just found out? We've just found out that K is unitary. Because why? Because the only way this can be 1 is if this is the identity matrix, because we know that psi dagger psi is 1. So K is unitary. Ta-da! And if K is unitary, that's the same thing as saying that probability is conserved in time. We also saw this exact same behavior in a number of other contexts, and I hope it's looking familiar by now. This is the same thing as saying that the H matrix is Hermitian. So this equals H dagger. H. i.e. H is Hermitian. So if K is unitary, H is Hermitian, and if H is Hermitian, then K is unitary. And physically what that means is the probability is conserved in time. So where did we see this before? Why should this look super familiar? We saw it with the translation operator. We saw it with the rotation operator. We saw it with, what was the translation operator, for example? Translation operator, can we call it T? Maybe we call it T. Translation operator was e to the minus I p sub, let's call this D. P dot D over H bar. And what we said was that the translation operator, which translated your quantum state forward an amount D, that this had to be a unitary operator, and that was equivalent to saying that P was a Hermitian operator. Sort of okay? So this should all look a little familiar. Whoop, whoop. Okay. Okay, so what do we got? We've got that this guy is Hermitian. We've got that we can get our probability amplitude for the events that we want simply by multiplying together a whole bunch of very, very short time segments and then summing over the different states that we have. Okay, now let's evaluate that probability amplitude. And you'll really like this, it's kind of fun. At least I think it's fun. Ah! And I'm the professor, so you just have to get on with it. Okay, pretty cool, huh? All right, so we're going to phrase this as a combinatoric problem. We want the amplitude for switching from left to right. Okay, and I want you guys to notice that if I overall have one switch, then the number of times I switch in each trajectory that obeys this rule has to be odd. If I switch an even number of times, I stay on the same side. So so it's an odd number of times that I switch. I'm going to write my Hamiltonian matrix, since I know it's Hermitian, as H equals, let's call this E naught for some energy. Big hint on what the H matrix is. And if this is symmetric, then we're going to have the same number here for being on the left or being on the right. The switching, we're going to call J. Now, it's certainly true that J could have an imaginary component. That is, although the thing would have to still be Hermitian. That is, this could be J plus IC, and this could be J minus IC. But right now, let's just, and we will have that for some applications. But right now, just to make it simple, let's just make a real Hamiltonian matrix. All right? So here are the different elements. Notice that if I switch, I get an element, I get this element, and if I stay the same, I get this element. So I'm going to write this as phi equals the number of times, the sum over all the different L's that are odd. L odd equals 1 to P. All right? And then we're going to have an amplitude of minus I j delta t over h bar to the L, because that's a factor that comes in for that I minus I over h bar h if I switch. So this is, L is the number of times I switch in any one trajectory. Still okay? If I don't switch, then I pick up a factor of 1 minus I over h bar delta t E naught. Now, how many times do I not switch? Well, remember that I've got n total steps. So if I switch to L times, then I have n minus L times intervals left that I didn't switch. Now, how many ways are there to arrange or to choose L out of a total of n? There's a combinatoric factor called n choose L. It's said out loud, n choose L. This is the number of ways you can choose L out of a total of n. So you've got n time segments, and the number of different ways of having exactly L switches out of n is n choose L. Okay? So the n choose L is n factorial over L factorial n minus L factorial. I just happen to know. If you didn't know, you'd look that up. Okay, so this is the amplitude for any one trajectory that has L switches. This is the number of trajectories that have L switches. But each trajectory that has L switches has exactly the same amplitude. Okay, we can actually compute this using the binomial theorem. Aha! So, this is a little trick. You're going to love this. So, define, what do I call it? I call it chi. Define chi as, this is chi, which is a function of j and E naught and delta t. And I'm defining it as L unrestricted equals 1 to n. Unrestricted. That is all the L's. Not just the odd L's, but all of the L's. All right? So L equals 1, 2, 3, blah, blah, blah. So we've got minus I j delta t over h bar to the L, 1 minus I E naught delta t over h bar to the n minus L, and we've got n choose L. So this is the unrestricted amplitude. This is the restricted amplitude. Now, I know what this is because from the binomial theorem, so binomial theorem. So from the binomial theorem, I can immediately get what this is. Just look it up. Right, so this is 1 minus I E naught delta t over h bar minus I j delta t over h bar raised to the nth power. Okay, now here comes the trick. Oh, you're going to love this. Notice that this thing that we want, phi, is actually equal to chi of j E naught delta t minus chi of minus j E naught delta t. In other words, oh, times 1/2, sorry. I'm going to pause while you guys look at this and figure that out. How do I know that? Well, what is chi of minus j? Okay, let's work it out, all right? So what is this here? This is I minus I j delta t over h bar raised to the nth power. Okay, if L is even, then this is 1. If L is odd, this is minus 1. So what does this minus this do? It gets rid of all the even ones. Isn't that cute? And since I know how to calculate each of these using the binomial theorem, I'm done. Is that cool or what? All right, don't all cheer at once. All right, so this is 1/2 1 minus I E naught delta t over h bar minus I j delta t over h bar to the nth minus 1 minus I E naught delta t over h bar plus I j delta t over h bar to the nth. I just plugged in minus j. Oops, forgot to close my bracket. It's pretty cool, huh? All right, I lost my next page, but how do I figure this out? I'm now going to let my delta t become very, very small. What do I get? In other words, I'm letting n go to infinity. Lim n goes to infinity. Well, it's actually pretty easy, right? Because as n goes to infinity, remember that delta t was my total time divided by n. Ugh. So this is t over n, and this is t over n, and so is this. Now what does it remind you of? If you have 1 minus x over n raised to the nth power. I know what you're thinking, Octavio, and it's right. Don't be scared. It's all right. This is the exponential. The limit as n goes to infinity is e to the minus x. Okay, so now I'm just going to take both of these limits, or excuse me, both of these terms in the limit that n goes to infinity. So that gives me 1/2 e to the minus I e naught plus j t over h bar minus e to the minus I e naught minus j times t over h bar. Or, that, so, all right, you can see that this is just e to the minus I e naught t over h bar over 2 times e to the minus I j delta t over h bar minus plus I j delta t, excuse me, not delta t over h bar. Still okay? All right. That's the amplitude, the probability amplitude for switching from left to right. So what's the probability? Amplitude squared. So what is it?
Cosine.
Oh, come on, there's a minus sign.
Oh.
Sine? Say sine. Yeah, it's the sine squared. So probability switch equals sine squared t over h. Cool, huh? Oh, goodness, I love that. Oh. Okay, now let's derive the Schrödinger algorithm. Oh, by the way, can you see how to get corresponding amplitudes for staying in one place? Staying on one side? No. Okay. Well, stare at it a little longer, and you'll see that the probability in time t for not switching is the cosine. So guess what? The probability for switching plus the probability for staying is 1. All right. You could do a shortcut here. Just say the probability for not switching has to be 1 minus the probability for switching, which again would give you the cosine squared. But I hope you see how you can do this algebra a little bit differently, so that the number you'd have an amplitude which would not be a sum over all odd numbers of switches, but a sum over all even numbers of switches. And then you'd add the two chi functions, and then you'd get the cosine. Everybody still okay?
Mostly.
All right, let's derive the Schrödinger equation. And she spells Schrödinger. I'm going to call it Schrödinger algorithm in honor of my boss because he always called it that. Okay, so suppose we have somehow calculated the amplitude to, as a vector, as a ket, to be in one of two places at a time, t minus delta t. So suppose somehow we know t minus delta t. And this is a ket. So this is right and left. So we've got two amplitudes. Amplitude for being on the right, amplitude for being on the left. Okay, then what do we know? We know that this must equal this matrix K that we've been futzing around on, operating on, and this is for going from time t to time, for going from time t minus delta t to time t times. In other words, this advances us in time. It's what Townsend calls, and everybody calls, the propagator. This advances us in time. Well, which is not terribly surprising since we've just sort of derived that it's e to the minus I h t over h1. So not terribly surprising. Okay, all right. So if delta t is small enough, we get a differential equation for psi. In other words, this is equal to 1 minus I h delta t over h bar psi of t minus delta t, which is psi of t minus delta t plus delta t times minus I h over h bar psi of t minus delta t. Okay, so now what I can do is take one term over to the other side, and I get this psi of t minus psi of t minus delta t, and divide both sides by delta t, and this gives me minus I h over h bar psi of t minus delta t, and this of course is d psi dt. Yay! We've just derived the Schrödinger algorithm. Whoop, whoop. Any questions about that? Okay, we're now ready to do the actual path interval. Okay. We found the propagator, otherwise called the kernel, otherwise called the Green's function, that takes us in time from one time slice to the very next time slice. We've done this only for a 2-level system, but that's okay. We can do this for an n-level system as well. Okay? And that's what he's doing with his A thing on page 282. Okay, so we're going to do a sum over trajectories, just like we did before. But now, instead of doing this, dot, 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 screen, what we're going to do is not just putting in a bunch of other screens, but cutting more holes in them. I'm just cutting holes. Now these are imaginary holes, of course, okay? So what we're now thinking of is not being on the left or the right at times delta t, but being in any of a number of different pieces along the screen. And we can call those places, what do I call them? X. All right, and that would be in a particular place at time t. So it's a multiple slit experiment in which we've got a whole bunch of holes. So we're now writing an amplitude to go from position A to position B in a time t as an integral over all the different individual places we could be for each screen. So this is dx1, dx2, dot, 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 dxn of k of a x1 delta t, k of x1 to x2 in delta time velocity, sorry. Dot, 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 k of xn to b in delta t. Now, I've written here integrals. Notice that this is exactly the same thing as what we had before, except we just had sums over being on the left or the right. So this was a, b, t, sum of alpha 1 equals left or right, sum alpha 2 equals left or right, dot, dot, dot. And then we had k being on the at a at and then going to alpha 1 in time delta t, k alpha 1, alpha 2 in time delta t, dot, dot, dot. So instead of a sum over being on the left or the right, we now have an integral because we're putting in an infinite number of these little holes. So not just infinite number of screens, but infinite number of holes. And they're just imaginary holes, and they were imaginary screens anyway, so it doesn't really matter. Okay, so what does that give us? Well, it would give us something more if I had the right notes. Here are the right notes. So we successively remove more and more material until we get the continuum, and that gives us n goes to infinity, or and remember that delta t was total time over n. This becomes the path integral, which is always written with a script capital D. He has a cute one in the book, and this is a sum or an integral over all different possible paths that we could do. So this is square bracket x of t. So x of t is a particular path, right? And and we're now integrating over all possible ways of getting from A to B in a time t. And we rate the integrand as, e to the minus I over h bar, let's just write it as h t. So that's how we get the path integral. And now we're going to do a simple example to make it all clear. And the simple example will be the free particle. At least I hope it'll make it all clear. Townsend does this as well. His derivation is different because he assumes the Schrödinger equation and just builds from there. We haven't done it that way. We've done it Feynman's way, where we're just building up the amplitudes. Okay, so example. Oh, and this example is also in Townsend, as I was just saying. The free particle, this is section 85. I'm doing things a little bit out of order. Free particle. Okay. Okay, so if it really is a free particle, then there's nothing to distinguish between one piece of space and another piece of space. Right? It doesn't care where you are. All right. So space is isotropic, which means that the Hamiltonian can't be a function of space. That's right. So Fp implies H not a function of space or time. Okay. So nothing can distinguish any particular direction from another, okay, if it really is a free particle. So the only thing that can possibly depend on is where you are, or were, one instant before. So it could depend on that. And so what we're going to say is that the k, from going from x1 to x2 in a time delta t, might be some function of the time, and actually it is a function of the time, times some exponential, which is only a function of the distance between x2 and x1. And it can't depend on the direction, okay? It can only depend on the distance. So we're going to say that this is I over h bar, some other function of time, times x2 minus x1 squared. That is, there can't be a linear term in x1 or x2, because then the Hamiltonian would depend on where you actually were. All it can depend on is the difference between between one position and another. Okay. So that means that if we've got a long time, that is our phi here, for going from x initial to x final in a time n delta t, well, that's going to be the function of delta t to the nth, right? Remember, we have to multiply all of those guys together. And then we've got the integral dx1, dx2, dot, 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 dxn minus 1 of e to the I over h bar sum j equals 1 to n of xj minus xj minus 1 squared, and times this function which we don't know. we're going to derive what A and F are. And we're going to see that we get exactly the same answer as Townsend. All right. Now, this is a multiple Gaussian interval. Before I take the limit n going to infinity, it's just a bunch of Gaussians. Okay? Can you see that? Because we're integrating out all the intermediate points, and all the intermediate points are Gaussians. They go like the square. But it's a little tricky because they're linked one to the next. That is, 1 is linked to 2, and 2 is linked to 1 and to 3, and so on. Right? But this is something that we're used to in physics. This doesn't faze us much, because why? Because this is the method of normal modes if you're doing vibrations in a crystal, or this is Fourier analysis if you're doing spectroscopy. This is something we know how to do. Okay? How do we do this? Well, this is a convolution of two Gaussians. Each time we have an intermediate point, it's linked on one side to the one before, and on the other side to the one after. And that's called a convolution of two Gaussians. Everybody sort of okay? Let's creep up on this so that it's clear to everybody by just doing n equals 2. In my next life, I'm going to be tall. You've heard me say that before. Okay, I want to point out that this is intimately related to the first problem in your P-set from this chapter, which is problem 8.1. So you might want to pay attention. Okay. So let's look carefully at n equals to 2. And then we'll wave our hands and say for any n, it therefore goes like this. All right, so k, phi, sorry. Phi for 2 delta t. And we're going to just pretend that there are only 2 time segments here. So this is going to be f of delta t quantity squared. And we're only integrating out one point, the intermediate point. Okay? So we're going in 2 steps. We're going from xi to xf by way of x1. Is that clear? And we're just integrating out one intermediate point. Okay? So this will be integral over x1 of e to the I over h bar a of delta t times xf minus x1 quantity squared plus x1 minus xi quantity squared. Okay, now xf and xi are not being integrated over. They're not a function of x1, so I can take that stuff outside. And then I get this f squared, and then e to the I over h bar a of delta t times xf squared plus xi squared. Those are the 2 things that I don't need to worry about. And then integral dx1 of e to the 2I over h bar a. Just remember that it's a function of time. x1 squared minus x1 times xf plus xi. So far, so good? Okay, now we're going to complete the square. Or equivalently, we just look up the integral for a Gaussian with a linear term, which is done for you in appendix something or other. I'll find it. Yeah, Gaussian integrals in appendix D. And And there we've got integral a, b equals integral minus infinity to infinity. This is just definition. This is equation D5 in your back of your book. Dx e to the minus a x squared plus bx. And you can see that this is exactly of that form. And he takes you through the steps of how to derive what the answer is. It's only 2 lines, and I urge you to look it up if you're at all interested, and it is kind of cool. All you're doing is completing the square. Okay? So you're rewriting this as y squared times something, right? So that means that you can just write down what you know the answer for a Gaussian is, and this is e to the b squared over 4a times square root of pi over a. So this is, and that's, yeah, so that's in your appendix. So I'm just going to pretend that we already knew that and write it down. And so this whole thing equals, I need some more space. So ignore this. So this is equal to f squared square root h bar pi over 2I capital A x of I over h bar a over 2 xf minus xi. So in other words, every time I do a Gaussian, I'm doing an intermediate point between 2 other points. What happens when I do that? Well, I generate a Gaussian between the 2 points that I didn't do. So every time I integrate out an intermediate point, it just gives me another Gaussian. Integrate out another intermediate point, I just get another Gaussian, and so on. Everybody sort of okay? Okay. I'm going to stop there, ask if there are any questions, and then pick this up on Wednesday if there aren't. And even if there are. But we are most of the way towards getting there. Cool, huh? Yeah. And as I say, your problem 1 from your assignment is essentially this. Okay, see you Wednesday.